Welcome back. We're doing section 20.10 right now, and we want to talk about carbon nucleophiles. Okay, so carbon nucleophiles. We've already experienced Greenyard reagents. Okay, so I will review Greenyard reagents. That's a bit of review. And the new thing today will be cyanohydrins. Okay, cyanohydrins are important. They're intermediates for making polymers, pharmaceuticals, and other molecules that might be of interest. So let's talk about Greenyard reagents. We've learned before that if we have a ketone, an aldehyde, or an ester, but we're just focusing on ketones and aldehydes right now. If we have a ketone, we can treat this with a Greenyard reagent. I'll color code that methyl group so it stands out here. Okay, so methyl magnesium bromide is a Greenyard reagent. And we have, normally we add just, water in the workup step. Some textbooks might say H3O plus. And what you're going to form here as a product is a methyl group is added, okay? And this works great for ketones and aldehydes. Let's do maybe benzaldehyde here. Okay, and let's do, I don't know, ethyl magnesium bromide. There are no limitations, pretty much, in terms of the R groups you can use for Greenyards. It can even be a tert-butyl group or something like that. So let's highlight this so it stands out. Okay, so we've got ethyl magnesium bromide, water in the second step. And let's draw out what we have here. And this can confuse students a little bit, but so here's the alcohol that we're forming. And we've got the CH2CH3 group here. Now, some students get a little confused. They think that this hydrogen is being replaced by this ethyl group, but that's actually not the case. That hydrogen is still attached to the molecule. It's still there on that carbon, okay? We're adding the ethyl group. We're not replacing or substituting the hydrogen, okay? So these are nucleophilic addition reactions. Let me take you through the mechanism. This is reviewed in section 13.6. Okay, in 13.6 they review how to make Greenyards and how they react with ketones and aldehydes to give tertiary alcohols and secondary alcohols respectively. Okay, but let me just review again here really quickly. I'll pick acetone, okay, and we'll do phenyl magnesium bromide. And this will make this molecule here. All right, so phenyl is pH. And that's a 6-membered ring, okay? We'll see. That's benzene, but when that's attached to something like a Greenyard, magnesium or something, then we call it a phenyl group, not benzene. So let's take a look at step 1. In step 1, we have attack, okay, attack. And what we have is a phenyl magnesium bromide, and we can basically draw the carbanion, okay? So if you have RMgBr, that's the same thing as R minus, and that's the nucleophile. All right? So that's what we call a carbanion. A carbanion is a carbon that's negatively charged because it has a lone pair. And so what we want to do is attack. This is very similar to hydride reagents, right? We attack the carbonyl, electrons move up to the oxygen, and you get the alkoxide that's formed here. And so we've added this phenyl group now. Okay, so this is a carbon-carbon bond-forming reaction. And then what we have is workup. We add water to this, okay, and the alkoxide here is going to become it's going to become protonated, and we form the neutral tertiary alcohol. Okay. So in some cases, your Greenyard provides the bulk of the carbon atoms, like in this example. In other cases, you start with a very complicated, huge molecule, and you just add a small methyl group or something, okay? So that's the mechanism. You have attack and then protonate, just like we saw with the hydride reagents, okay? Okay, here's problem 20.33 in the second edition textbook. And so again, you want to identify the parts that you have. Here's our ketone. And then we want to add an ethyl group there, okay? So this is a nucleophilic addition. So we want to add an ethyl to the carbon, and we want to add an H to the oxygen and change it to a single bond. So this is essentially just a drawing activity to predict the major product. So we're going to form, so the phenyl group is attached to the carbonyl carbon, okay? The ethyl group is attached to the carbonyl carbon, and we're adding an ethyl group. So an ethyl group is just 2 lines like that. And then we change that carbon-oxygen pi bond to a carbon-oxygen single bond as an alcohol, okay? So maybe be better if I changed this, highlighted ethyl group to a green highlight, okay? So you can kind of see. All right, so anyways, in the next one, okay, so here's phenyl, okay? We've talked about what phenyl is. It's a 6-membered ring with some double bonds. And here's our carbon-oxygen pi bond. So in our drawing activity, what we want to do is sketch out everything that we have here. You'll never be marked wrong if you draw hydrogens in your class. So if you're just starting out, you might draw the hydrogens. So here's a phenyl group attached to the carbonyl carbon. Here's a hydrogen attached to the carbonyl carbon. And then what we want to do is we want to add a phenyl group, right, which is a 6-membered ring, to that, okay? So I'm adding it in green. Let's see. Okay, so green would be here. So there's my phenyl group that I'm adding, okay? Now don't forget your alcohol. There's going to be a carbon-oxygen single bond, and we write that as a hydroxyl group, okay? So if we clean this up, it would look like, something like this. Okay. All right, so this one here, what we need to do is we need to think carefully about what's happening. So we're going to add a phenyl group, okay? We're going to add a phenyl group to the carbonyl, okay? Whoops. And if you're attentive to detail, you'll notice here that there's a slight change in the way they're indicating the workup. Here we just have neutral water. Here we have neutral water, and here we have H3O plus. So watch out. H2O in the acid is going to neutralize the alkoxide to give you the alcohol, okay? But we also have H plus present, which is going to hydrolyze the acetal. And that's 20.6, I believe, if I remember the number, okay? So this right here is a protected ketone, and that's going to be revealed when H3O plus hits that, okay? So what we want to do is sketch this out. So we want to draw this 6-membered ring, okay? There's a methyl group attached to that carbon. We draw the alcohol as usual, and we draw our phenyl group that we're adding as usual. So it kind of looks like problem B here, okay? We're adding phenyl, and the ketone changes to an alcohol, okay? But now you need to pay attention to this carbon here that I've placed an asterisk on, okay? That's at this position here. And so remember, those 2 carbon-oxygen single bonds are cleaved off, and we generate a ketone, okay? So I'll make that in a different color, okay? So you might look at the hydrolysis of acetals. That's another reaction we've learned, okay? So pay attention to that. It's a deprotection of a ketone. All right, enough about Greenyards. Let's talk about cyanohydrins, okay? So cyanohydrins have this functional group. Okay, it can come from an aldehyde or a ketone, and this is called a cyanohydrin. Okay, so anyways, if you have acetone, for example, and you treat this with sodium cyanide, okay, with a catalytic drop of acid. So the textbook uses those little, brackets, a drop of acetic acid, for example. Now, normally you don't want to react cyanide with strong acids because that's going to form cyanide gas, which is very toxic. They use that in the gas chamber in some states. So sodium cyanide in the presence of small amounts of H plus is going to give you a cyanohydrin. This, I bet, is a reaction you're not doing in your lab because there's some toxicity and dangers involved with that, okay? So at equilibrium, you can isolate a 78% quantity of this cyanohydrin, okay? So sodium cyanide in water, it's in protic solvents, there's H plus present, okay? Now, the mechanism is shown here on 20.12. Okay, and the reagents that they normally show are just it gets weird. Okay, so this is completely correct and so on and so forth, but I just want to show my modified mechanism. And the modified mechanism I'm going to show is H plus being used in the first step of the reaction to allow students to place things into two categories. Okay, so this is going to form trying to erase this. Okay, so this forms the protonated guy here. Okay. And then cyanide can attack here, okay, to give you the cyanohydrin, okay? Now I like this modified mechanism because it teaches students that if you have an acid, use that in the first step of your mechanism, and it helps them just focus on kind of the patterns instead of trying to remember when do you use this mechanism, when do you use that mechanism, okay? So I would accept protonation, then attack, or in the textbook, they attack, then protonate, okay? When you have really weak acids, you can have attack occurring before protonation, and the same thing happens in amines, okay, when you have a catalytic acid. But this is fine. Any mechanism you propose is going to be fine. Attack and protonate or attack in my class, okay? So that's a little bit about the cyanohydrins. What can cyanohydrins be used for? If you take acetone and you treat this with sodium cyanide with catalytic amounts of acid, you'll form the cyanohydrin as we mentioned. Okay. A cyanohydrin is a carbon-nitrogen triple bond. Okay, it's a nitrile or a cyano group there. And what you can do is treat this with acid and a bit of heat, okay, to dehydrate. And so what you form is this here, okay? And you can polymerize this to make nitrile gloves, for example. That's just one use of this polymer, but you're familiar with the purple gloves or the blue gloves people use, maybe in the doctor's office or something like that, as opposed to latex. Okay. You can also take this molecule and treat it with a large excess of sulfuric acid, tons of water, lots of heat, okay? And this will hydrolyze the nitrile. We'll learn about this, I think, in chapter 21, to a carboxylic acid, okay? And you can polymerize this to make a I forget the name of the polymer. You can polymerize this to make a polymer that's super absorbent, okay? So that's used in feminine care products, diapers, certain absorbents and things like that, okay? So this will make that. So still trying to remember the, try to remember the name. So anyways, there's lots of different uses of this and pesticides and other kinds of things, okay? So very simple starting materials, okay? Going from acetone to a rubber glove is pretty amazing, okay? All right, so let's talk about some practice problems here in the book to see what we need to know how to do, okay? So problem 2035. Okay, so problem 2035 reviews your knowledge about what you can do with nitriles. So if you have a nitrile and you treat this with LAH and water, you will convert the nitrile to a primary amine. I dislike how Klein introduced the synthesis of amines in the aldehyde and ketone chapter. The synthesis of amines is much later in the book, and I defer memorization of this reaction until we get to there. But we'll just go ahead and deal with this, okay? So let's talk about problem A here. We've got this ketone, and in the first step, we're using potassium cyanide and HCN. So HCN is the acidic form of the cyanide, and that's the catalytic acid there. So that's going to make the cyanohydrin. So let's just sketch this out. First, we're going to form the cyanohydrin. Okay, and then in steps 2 and 3, we're going to do this transformation here, where we're converting the nitrile to a primary amine. So we want to take our 6-membered ring, okay, and what's kind of tricky and hard to notice is that there's actually a carbon in CN. So there's a carbon right here that I'm dotting just to make sure that you pay attention to and don't leave out accidentally. So it's going to make that primary amine, okay? So it's an amino alcohol technically. In part B, we're going to, in the first step, form the cyanohydrin, okay, the cyanohydrin. And I'll just sketch in the hydrogen there in case you're a little bit uncomfortable with me leaving off that hydrogen. So here we form the cyanohydrin in step 1. And then in step 2, we're going to add H3O plus and heat. And what the textbook teaches you is to draw the carboxylic acid. Once again, I do not like talking about the hydrolysis of nitriles here in this chapter because it's something we talk about in the carboxylic acid chapter. Okay? But if you treat this with H3O plus and heat, that's going to go on to make the carboxylic acid. When you draw the carboxylic acid, make sure you keep the carbon of the nitrile there and don't leave it off by accident. So we're going to draw a carboxylic acid here, and I'll go ahead and I'll put that hydrogen back in the middle so you can see that it hasn't disappeared or something like that. Okay? All right. So that's a little bit about the cyanohydrin. There's not much to talk about. When we get to carboxylic acids, you're going to have to remember this. So you might just put a little bookmark or a tab in your textbook and refer to this later when we talk about carboxylic acids. Okay, we are still in section 20.10, and the most important thing, so we've talked about Greenyards and how they can make secondary and tertiary alcohols. We've talked about cyanohydrins and how that's made from toxic cyanide and some kind of acid catalyst, okay? The third thing I forgot to mention that we need to talk about are the Wittig reagents. Okay, of course, German, the W sounds like a V sound, like the Volkswagen cars we're familiar with on the street today. So, Wittig reagents won George Wittig the Nobel Prize in 1979, and it's a very useful reaction for forming alkenes. This is what it looks like in a nutshell. If you have a ketone and you treat it with an Irid, this crazy looking reagent, let's see, what should I use? I'll use a this guy here. I'll draw it all out so you can kind of see what it looks like. That P is a phosphorus and the pH is a phenyl. So please do not forget that a phenyl ring is a six-membered ring, attached to something, okay? And what you make from this is an alkene with your carbons added in there, okay? So here we have an ethyl group kind of looking thing, and then here we have 2 carbons, okay? And there's some side products here and so on and so forth, okay? So this thing is called an Irid, and first I just want to show you the mechanism before I show you how to form it, okay? And so that's Irid, Y-L-I-D-E. It just sounds so strange, it's hard to pronounce, it's weird, and it's a weird chemical. But basically, it's something that has a negative charge on one atom and a positive charge on another atom, and there's a resonance structure you could possibly draw between them that shows, a neutral form with an additional double bond. So in the molecule I showed before, we had this weird looking thing that looks like this. Okay? So we have a negative charge on carbon. It looks like a carbanion. And we have a positive charge on the phosphorus. Okay? And we can draw a resonance structure that shows how the electrons are stabilized here. And we form a double bond between the carbon and the phosphorus. And here you can see how phosphorus exceeds the octet. That apparently is okay because phosphorus can expand its valency to include d orbitals in extra bonding to make more bonds. So this right here on the right, it has a double bond. It has no charges. Okay, but these are resonance structures. So this is what we call an Irid. Okay, an Irid. So this is going to be the thing that attacks, okay? If you have a carbanion, this is a carbon nucleophile, that's a negative charge on that carbon, that's the thing that's going to be attacking. So this is going to be your nucleophile. And remember that positive charges are generally electrophiles, right? This is an electrophile. So I like to tell my students an Irid is a lot like Dr. Jekyll and Mr. Hyde, or if you haven't read the book, like Two-Face from Batman, he has good days and bad days based on how he flips that coin. An Irid has 2 characters, okay? It's going to be nucleophilic at the carbon, and it's going to be electrophilic at the phosphorus atom. So let me show you how this works, okay? Let's do this chemical reaction here. By the way, we sometimes call these metathesis reactions because you can see how, the carbon-oxygen double bond now becomes a phosphorus-oxygen double bond. And the phosphorus-carbon double bond changes to a carbon-carbon double bond. So, they kind of switch partners, okay? So we sometimes call this a metathesis reaction. I'll remove those scribbles to make this more simple on the screen here. So what we want to do is we want to show the Zwitter ionic form of the Irid. Okay, so first we draw the carbanion. Okay, and that's, you know, bonded to a phosphorus and 3 phenyl groups. I'll draw them all out here so we don't get confused. Okay, and so what we want to do is attack the carbon atom of the ketone, which is the electrophile. Okay, so remember again, I'll sketch it out. Negative is the nucleophile, and it's delta plus on this ketone, so that's the electrophile. Okay, so that's A for attack. Okay, so we've added our CH2 group here. And we've got the phosphorus. I probably should, let me fix the color so you can see which parts come from which molecule, okay? So in yellow, there's my acetone fragment, and it's now bonded to the carbanion part of the Irid. So here's my CH2, and it's bonded to the phosphorus and the 3 phenyl groups, okay? Okay, so that's the intermediate there. And this here then is going to, so negative and positive are attracted to each other. There's different mechanisms that you can show for this. Okay, I don't require you to memorize this if you're in my class, but I just do want to show this. Okay, so in case you're a science major, you don't get lost when someone expects you to remember, well, that's just like this enzyme reaction or something. Okay, so we have an oxygen phosphorus bond, and this is known as an oxaphosphatane. Okay, it's a kind of a reactive intermediate, and now what happens is we move the electrons around in the ring like so. So we move these here and these here. Just pay attention to which way you're moving it and make sure you're doing it the right way. So we're going to form an oxygen phosphorus double bond. Okay. And this is waste. We don't want this, but it's a huge amount of carbons. And we form the molecule that we do want, the alkene. Okay, and I'll color code that correctly here with the CH2 group. Okay, so that's this molecule right here. So we go from ketones to alkenes. So how would I classify this? I would classify this as attack, I guess attack, and then here eliminate. Okay, but again, you don't need to memorize this, okay? Now, what I do want to talk about is synthesis. You definitely need to know the synthesis. And it's 3 steps, okay? It's 3 steps to go from a ketone to an alkene, all right? And counterintuitive, it does not begin with the ketone. So for example, if we're trying to figure out what reagents we would use to do this, what do we need to do, okay? First, what you need to do is remember that this is what you're operating on. You're operating on the carbonyl, and you want to count your carbons, okay? There's 1, 2, 3, 4 carbons, okay? As usual, when you have a carbon-carbon bond-forming reaction, count your carbons, carefully consider the branching and things like that. So what we want to do is first start with the 4 carbons, and you want to slap a leaving group on there, a bromine, okay? So you want to start with a alkyl halide. And remember again that primary or secondary alkyl halides are going to be best when they do SN2 reactions, okay? So this is triphenylphosphine. It looks a lot like ammonia. You know, phosphorus is below nitrogen in the periodic table. It has 3 bonds and it has a lone pair, so it's going to kick off the leaving group. And this is the strange thing here, as if there's not enough strange things going on with these reactions. but it's a salt, okay? The phosphorus has a positive charge, and the bromide is floating around. So that's a salt, all right? And so we isolate this, and then we treat this. So this is step 1, okay? In step 2, we treat this with butyl lithium. Okay, so let me just name these chemicals in case you're kind of losing track here. So this is triphenyl phosphine, and this is called butyl lithium. It's a lot like a Greenyard reagent. It's a strong base. So let me draw a hydrogen here. And let me sketch out butyl lithium. So it's a carbanion. I'll just draw the lithium as a ion and the carbanion as an ion. And what I want to do here is use it as a base to remove that proton next to the phosphorus. And what I get is the molecule that looks like this. And that, folks, is what we call the Irid. So that's how I make the Irid. So step 1, take your alkyl halide triphenylphosphine, make the salt. Step 2, add butyl lithium. We have our Irid. And then step 3, we add our ketone. Okay, step 3, we just add the ketone, in this case cyclohexanone, and that makes the target molecule. I'll draw it out again. Okay. So 3 steps, all right, 3 steps. Let me sketch that out here as a kind of a general thing. Okay, so step 1, you're going to add triphenylphosphine. So that's phosphorus, and this is phenyl. Okay, so it's called triphenylphosphine, and that's going to make the salt. Okay, and R can be anything you want. Remember, again, it should be primary or secondary. And then if we treat this with butyl lithium, that's going to make the Irid. Okay, so we're removing 1 hydrogen or 1 proton from that carbon. Okay. Sometimes it's easier just to draw it as a double bond. So that way you could remember which bonds are kind of moving around in the metathesis. So either of those resonance structures you can draw. And then step 3, you add your ketone. Here I'll have to use a different color to make it kind of easier to see things. So again, remember that you're going to replace this carbon-oxygen double bond with a carbon-carbon double bond. So you're going to take all of this business and you're going to move it up to here. Okay, so let me draw what that gives you. And here again, we're just using the color to help keep track of the groups. So there's my molecule, that's my carbon atoms of my ketone, whatever that is. And then I'm going to doubly bond it to that CH and that R group. Okay, so I'm basically in white circle here putting this whole group in there. Okay. So those are the 3 steps, okay? So you want to add triphenylphosphine. Step 2, add butyl lithium. Step 3, add your ketone or aldehyde, okay? And you really want to pay attention to the synthesis. Use retrosynthesis to solve these problems. So a great practice problem is 20.37, 20.38, there's just a lot of different practice problems here, okay? So 20.37 is a great practice problem. Let's do that one here. All right, so problem 37 says identify the reagents necessary to prepare each of the following compounds using a Wittig reaction. So again, each one of these problems is going to require 3 steps. The way you solve these problems is to split, I can't see that color very well, you split the carbon-oxygen pi bond, the carbon-carbon pi bond, and then you want to pick the left or the right depending on the substitution, okay? This carbon right here has less carbons attached to it, so we want to make that the alkyl halide, okay? So, for example, you could break it down like this. That's secondary, that's more sterically hindered. Or you could break it down like this. That's primary, that's less hindered, okay? So you want the less hindered primary alcohol, the primary alkyl halide, and the more substituted ketone, okay? So here's the ketone, and then you want those 2 carbons to be attached to a leaving group, okay? So the synthesis here for part A is going to be start with your ethyl bromide, okay? Treat it with triphenyl phosphine, treat it with butyl lithium, and then in step 3, add your ketone, okay? And that's going to give you the target molecule. I'll just draw it in case this is very confusing for you, okay? So retrosynthesis is the way to solve these problems. Let's do another one. Let's do molecule B, or problem B. So we want to split this carbon right down the middle, okay? And we want the less substituted carbon to be our alkyl halide. The one on the right has 1 carbon, so we want to make that CH3Br, okay? That's, we want to stick bromine on 1 carbon, so that's what we have. And then the other side you want to be our ketone, okay? There are 7 total carbons there, 7 total carbons, so it's going to be like this, okay? It's going to be an aldehyde. So for problem B, we want to take bromomethane. We want to treat this with triphenyl phosphine, butyl lithium, okay? And then we want to add the rest of the number of carbons in the form of an aldehyde, okay? An aldehyde. And that's going to give me the target molecule there. Okay. Let's do part C. Okay, part C. We again want to break this carbon-carbon pi bond into a left-hand portion and a right-hand portion. On the right, we have just 1 carbon, so that's going to be 1 carbon attached to a halogen. Bromine's a good leaving group. And then the other part of the molecule is going to be my ketone. Okay, going to be the ketone. So make sure you have the correct number of carbons. And so what we want to do here is the same sorts of sequence of events. We want to start with the alkyl halide. Step 1, triphenyl phosphine. Step 2, butyl lithium. Bu stands for butyl. Step 3, add my ketone. In this case, it's cyclopentanone. And that's going to give me the target molecule there. Okay? Let's do part D. In part D, once again, you want to split this guy down the middle, and you want to identify the less substituted carbon. So this guy right here is the less substituted carbon. We want to put a halogen on that dotted position, okay? So that's going to be, here's my dotted position, put a bromine there, okay? And so once again, you're going to treat this with triphenyl phosphine. You can see how it's very similar to all of these other problems. But what ketone are we going to be reacting this with? You need to very carefully draw this whole thing out with those weird isopropyl groups. And the carbon-oxygen double bond is going to be right, let's make it a different color, on this red dotted carbon. Okay, so that's where your carbon-oxygen pi bond is going to be. So step 3 is going to be add that funny looking ketone. Okay, and that's going to give me the target molecule. That's too difficult to redraw, so I'll just draw it in there. Okay. All right, in molecule E, once again, you want to break this molecule down the middle, and you want to identify the less substituted carbon. The carbon on the left is less substituted, so that's going to be the alkyl halide. That's going to be benzyl bromide. Okay. I'm going to treat this with triphenylphosphine. You know the drill, butyllithium. And then what ketone is that going to be reacted with? We're going to react it with a 6-membered ring that's doubly bonded to a ketone, or cyclohexanone, right? Cyclohexanone. So step 3 is going to be cyclohexanone. And you could even draw the carbon-oxygen double bond pointing in the direction that you think might make more sense to you. So that forms the target molecule there. Okay? The textbook says try problems 20.51 through 53. I urge you to try some of the additional problems in the back of the textbook. If you're watching my lectures, please note that I'm skipping section 2011 and 2012, which is 2011, which is the Baeyer-Villiger oxidation, okay? But I will review 2012 in my next video. Thanks for watching.